Hello, let's enjoy computing the Gaussian integral. The Gaussian integral is defined as the integration from minus infinity until infinity of e to minus x squared. Some of the subtleties that you should ask yourself is question 1. Is this number finite? So for example, a good exercise is to prove, for example, that this integral is well defined. So for example, show that the limit L going to infinity of minus L to L dx e to minus x squared again, that this is finite and exists and is finite. So one thing that could happen is it could be oscillatory. This function is not oscillatory, or it could be infinite. But of course, we know that this is finite. So the intuition here is that we have this Gaussian bell shape. And one very important thing to discuss is that this decays very fast. So make sure that you understand the intuition here. And this decay is so fast that you can always integrate this function. To understand this decay better, you can consider the question whether you can find integrals of the form x to power n e to minus x squared dx, and then on the real line. And in fact, this will also be always finite. And what this means is that the growth of any polynomial for any n equals 1 to whatever you choose, any finite n, will never overcome this Gaussian damping. So the decay here is very, very fast. And the meaning of this one is that Gaussian function decays faster than any polynomial. Again, you can ask yourself how to make sense of this. Once you have this, you can use linearity of integrals and then do this summation like this. And I can sum from n equals 0 to some degree d of a polynomial. Any polynomial is of the form n equals 0 until some finite d, some coefficient an, x to power n. This is a polynomial function. And this one, we can once more integrate over r and e to minus x squared. And then by linearity, we find that for any polynomial, this is finite. So this is the statement. Okay, so those are some questions. This is very useful because it allows you to extend this integral analytically. This might be useful for understanding how to define such infinite objects. And for irregular functions, and knowing how to do it for a regular function like a Gaussian, it might be interesting. It might be handy later on. And this is very useful to understand different behaviors in physics, engineering, and so on. So that's why it's worth looking into that. Okay, so the standard way of computing the Gaussian integral is to square it up and then use the Fubini's theorem, the correct Jacobian of polar coordinates, and basically take a square root. All this is based on the absolute convergence. So I equals integral over the real and dx e to minus x squared is a finite number. So if we square it, we can write this as once the integral and then again the integral. But nothing prohibits me from naming the second integral in terms of a different name of a variable. And then here, e to minus y squared. So the first ingredient is the Fubini theorem. And Fubini's theorem will allow us to write this integral as the integral over the real space, then d to x, and then e to minus norm of x squared. And here we have the entire real plane. So what does it mean? It means that we have two variables, x1, x2. Then we have a small volume, dx2, dx1. dx1, dx2 is a small volume element, and I'm writing it as d2x. So now we are going to some essentially volume integral, but this will be very helpful. But then again, you need to ask yourself, when does it hold? And Fubini's theorem tells you that the functions need to be integrable, need to be finite. So, so the assumptions that come in here are fairly simple, and yeah, they are satisfied. Yeah. Okay. The next thing is going to polar coordinates. So here we need to have the correct Jacobian. So second is polar coordinates or coordinates. And here we will have r cosinus phi x to r sinus phi. One issue that we have here is one subtlety that we always have to keep in mind is that around 0, the transformation is not invertible, because at point 0, r is equals to 0, and phi can be anything from 0 to pi. So it can be any angle on the point, because a point rotates into itself. A point on a circle doesn't rotate into itself. Okay, so good. Anyway, the Jacobian of this is equals to r, and so we can switch to the integration over the entire plane is any radius, and then an entire circle. So I need to go from 0 to 2 pi d phi. Then I need to enter the Jacobian, and then I need to express x1 plus x2 squared, and know that this is r squared. This is because you square all of this, sum it up. This will be r squared plus cosine squared times cosine squared sine squared, which is 1. So e to minus r squared. And now we were already discussing that this is again finite for the same reason now, but now there's a big difference, because if we take a derivative of the Gaussian function, then this is the derivative of the exponential, which is the exponential, and the derivative of the function inside is minus 2 times x, and then again the same function. So this we can compute by the chain rule of nesting of functions. So g of x is dx dxf of gx times the derivative dx g of x. Yeah. So because the derivative dx x is x, then we have this. Okay, so this is the derivative. And so if you look at this, if I would set x equals to r, then I see that here, this is exactly independent of phi. So now using Fubini theorem backwards, and again, in principle, you have to say that you're using the Fubini's theorem backwards and then times 0 to infinity dr r e to minus r squared. So I'm missing minus and 1/2. Here I get 2 pi. So what we get is I is equals 2 pi from the first integral. And then let's write it again. Dr r e to minus r squared, and the dr e to minus r squared is again the exponential times minus 2 times r. So we get that this is 2 pi times minus 1/2 times the integral 0 to infinity dr e to minus r squared. So now this is what we call the fundamental theorem of calculus, that we have minus pi, and then we need to insert the function below the derivative 0 to infinity. And now we need to use that limit of r to infinity e to minus r squared is 0. You could prove this by showing that e minus r squared is larger or equal to 0, but it's also dominated by e to minus r for large enough r. So can maybe compute this later. And we know that e to minus r goes to 0. So from both sides, e to minus r squared goes to 0. So what do we have? We have minus pi limit of r going to infinity, e to minus r squared minus e to minus 0. Just to be super clear. So we just said this limit goes to 0. Minus cancels with this one. E to 0 is 0, and we got our pi. So our squared integral is pi. So we get as required e to pi. Did I say that this is pi? No. Okay, this is square root pi. Good. So let's go in color through the subtleties. So one question is, when we write such a statement, is whether this will be finite at all, and how to prove this. One idea would be to use dominance by a simpler function that we know how to integrate. So for example, for large enough x, e to minus x squared is smaller than e to minus x. So this integral asymptotically is smaller than this. What does it mean asymptotically? Okay, so for x larger or equal than 1, so I can split the integral I to be the integral from -1 to 1 dx e to minus x squared, and then all the other summation. Because it's symmetric, we can go from 0 to 2, and then plus 2 e to minus x squared from 1 until infinity. And here we can substitute bounds, saying that e to minus x squared is smaller or equal than 1. And this one is, so I get smaller than 2 plus 2 times integral from 1 until infinity e to minus x dx. So this is smaller than infinity. So that's one thing. This is how we could prove that. Another thing is whether it converges, and that it converges we get from one important thing that we were using was that x going to infinity, e to minus x squared goes to 0. So at some point, the Riemann sum is summing almost 0. So in the end, it will converge. What else do we have? This was useful because we can also generate those polynomials as derivatives of the Gaussian function. So that's useful for other things. And basically, this is gradual improvements of questions of convergence. So first, does it converge at all? And then maybe we can ask how fast does it converge, and so on. And finally, we can ask about what if we have some added functions here. So the application of this one is, for example, stationary phase approximation. Will be of the form that, or for Laplace transforms, we might have some function f of x times e to minus x squared, and we want to know the integral of this. Okay, so this is one helpful thing that we can do here. Okay. So finally, we got the integral. Then the subtleties to study is the assumptions of Fubini's theorem. Then notice that we were using the Fubini's theorem backwards. Then this was 2 pi, which is just a regular integral over the circle. The angular variable integrated up over the whole circle is 2 pi. Then we were looking at the derivative, discussing the correct Jacobian. So the Jacobian has to come in here correctly. We need the correct integration borders, and that's it. Okay, and then we do the limit and obtain the computation. Good.